Hello, today we're going to be talking about enolates. How can we make an enolate? We already talked a little bit about what an enolate is. So if we take our carbonyl and react it with a base, and we're going to react with that alpha carbon here, we're going to form this species here. We get that negative charge there. This is going to be our enolate, right? This is our enolate. Enolate. And we notice about this enolate, it's kind of special because I can take this group here and I can do that. And I can make this, right? I can do this resonance structure of this, right? And why do I want to do a resonance structure? What do we know about resonance structures? This shows that we can delocalize this electron density between this carbon here up to this oxygen, right? Electrons are moving back and forth in here, which is important because it helps to tell us that this is actually somewhat stable, right? It's somewhat stable. This also tells us that this carbon here, since this is stable, this hydrogen here is actually the pK is going to be a little bit lower than normal, right? What's the pK of that going to be? We mentioned it in a previous video, and I'm sure you watched those videos all together in order. You know the pK is going to be around 20, right? Which is actually fairly low, right? If we think about a regular CH bond, that pK is around 50, right? So we're down pretty low. We're down in the 20s. So that's a pretty good place to have that to be. So it's somewhat acidic, meaning that we can pull off the proton and we can generate this enolate here, right? And what's nice about this enolate is that we can use this to do what? We use this as a nucleophile to attack things, okay? But before we can use this as a nucleophile, we need to figure out how to make it and what base we're gonna work with, right? There's also different types of enolate that we can make, and we can talk about those ones, right? So let's look at some bases that we can use to make our enolate. So we'll start down here. So let's go back to our carbonyl example. Have a hydrogen here. We know the pK is going to be about 20. So what bases do we want to use? What are some common bases? Well, let's use, how about ethoxide? This is an O directly attached to a CH2, CH3, right? Ethoxide, that's ET, meaning CH2, CH3. Let's pull off this hydrogen here. We can do that. We get that negative charge there, we get our man, plus we get HOET, okay? Now, look at this one, pK. What's the pK of that alcohol there, right? We've made an alcohol now, HOET. This pK is gonna be what? It's actually about 19, right? So it's actually fairly close to our pK value of this one here, right? It's actually a little bit more acidic than this pK here. So which way is equilibrium going to shift, right? This is actually going to be equilibrium. So we got to change our arrow here, and we're going to use this type of arrow, right? And really, since this pK value is slightly lower than this one, it's actually going to shift equilibrium going in this direction here. So technically, we're going to have more of this in solution, right? We'll have a little bit of this in solution, but a lot more of this in solution, right? And so this is okay if we want to use this base here. It's not that strong relative to our enolate, but it's a way we can make maybe a little bit of this a little bit at a time. The reaction would be kind of slow. It wouldn't go very fast because as we're using this base to deprotonate this, it's not working as well, right? It's not a very strong base, okay? So we make a little bit at a time that keeps reacting. So this is okay using this type of base, but the problem is we're not going to make a lot of our enolate to use for the next step, okay? So that's one type of base we can use, our sodium ethoxide. So let's think about maybe another base we can use. Maybe a base that's going to be a little bit stronger, right? So let's look at a different base to make enolate. How about sodium hydride? How about this one? So I take sodium hydride. Remember, sodium hydride, sodium's a positive. This is the one time where you have a hydrogen. It's got two pairs of electrons. It's got that lone pair there. It's going to be fairly basic. This is going to take off that proton. And we get this. And the cool thing about this is that when this hydrogen picks up this proton, what are we making? What's going to be our conjugate acid? It's actually going to be H2, right? And that's a gas. That's going to go away. So that's pretty cool. So in this reaction here, our pKa is going to be 20, like as we talked about. What's the pK of H2? the pK of this one is actually going to be around 35, right? So that's pretty high. So if we see our pKs now, which way is the equilibrium going to favor? It's actually going to favor our right side, this direction, right? Because this is going to be lower pK. This is going to be the more acidic. We're going to favor and get more of this one. So this base is stronger. And if we use this base here, we have more of a chance of making all of our enolate, right? We make all the enolate. Or in this case here, we're going to have this equilibrium of both of these. So we want to use our stronger base here to get just our enolate form, okay? Just get our enolate form. So this is a better base to use. There's one more base we can work with, right? There's one more base we can use that hopefully will drive the reaction to give us just the enolate product, right? So we use sodium hydride. Another one that's common to use in organic chemistry that we use a lot of times, chemists use, and I'll erase these ones here, is going to be, we'll take our carbonyl, our hydrogen, and now we're going to use a new one. It's going to be LDA. It's lithium diisopropyl amide, right? And again, we'll just write LDA. It's a little bit simpler. We can draw the structure of it. And it's lithium diisopropyl amide. And so we're going to have a lithium complex here, right? It's a salt. And so we have this, it's called LDA. Now, what's interesting about this base is that we have the nitrogen here, it's negatively charged, right? So this is where it's going to take the proton from. But also, look what's attached to that nitrogen. We have two isopropyl groups in there, right? And we know about this already by having these groups attached to nitrogen. These are going to be our bulky groups, right? By having our bulky groups here, that's going to block it, so it's going to be a strong base. And then it's going to be a what? Weak nucleophile, which is great. It's going to be a strong base. It's going to be a weak nucleophile because these bulky groups are getting in the way. So it's a strong base and you can easily pull off this small little proton, but these bulky groups are going to get in the way that it can't make a new bond with a carbon, right? Okay, so it's going to be our strong base and our weak nucleophile. And so we can use it. And we can get our enolate there. And what's nice about this is that we can form our enolate here. And actually, when we draw in our conjugate acid, the pK of this one is going to be what? It's going to be around 40, okay? pK value of that one's going to be around 40. So already, again, we can see this idea that, what's pK of this one? It's around 20. So we can see that this is going to be the more acidic proton that we're going to pull off relative to our conjugate acid proton. And we see that the equilibrium would shift completely over to our enolate. We'd have a lot of this enolate being formed in solution because, again, we're using that very, very strong base, okay? So in most cases, when we want to make that enolate, we want that enolate to be formed and then do something else with it. We're going to use LDA or we use sodium hydride, right? LDA is pretty common. It's one we use a lot for organic chemistry to make our enolate there, right? Another one you'll see, like we talked about with our first example, is sodium methoxide. We can use that, but that's reaction going to go a lot slower. Remember, because it's in equilibrium between the enolate and forming, between enolate and coming back to forming this acid version species as well. Okay, that's more in equilibrium. Okay, so in most cases we'll use LDA, and we'll show some examples where we can use sodium methoxide or sodium methoxide. Okay? So this is how we can make our enolates. Now let's look at a couple more examples of enolates here. So we learned about how to make them. We know what bases to kind of work with here, the three main bases. Now let's look at a couple different types of enolates. All right. So we talked about the standard one, but we can also have another type of enolate. So what if I have this R here, this group here, and remember, I have this nitrile group. We talked about the nitrile group already. It's a little bit special, right? And what if I have a hydrogen here? Well, again, I can use my base on this hydrogen. And I can make that negative charge here. This is going to be kind of like enolate-like, right? Where again, we have this alpha position here. We can make this enolate here with our base. So we can make negative charge here. This can be fairly nucleophilic, and we can attack things, right? So this is another type of enolate that we can work with, right? Deprotonate it, make your enolate. This can be a good nucleophile. What's some other type of enolates? Another one we can make is, how about this one? Notice this one here. Now we have a carbonyl, 2 carbonyls attached to the same carbon here, right? And what it turns out with this one here is, again, this is going to have a proton that we can deprotonate. Now, the interesting thing about this is that the pKa value of this one is going to be what? It's actually fairly small. It's going to be 9, right? Why is it so low? Why is this pKa value so low? Well, because remember, if we do the resonance structure of this one, and we can do that with our base, again, we don't need a very strong base for this one. We get that negative charge there, right? On this lone pair of electrons is going to be in between these 2 carbonyls, and we can draw resonance structures of that, right? I can draw resonance structures of going like this. I can draw resonance structures all day, like that. Right, that's one resonance structure. Normally, this is the kind of resonance structure we see with our normal enolate, right? With 1 carbonyl. I also can do this. Electrons can come back down. How about going this direction? Notice how this negative charge is spread over multiple atoms, a lot of atoms. The more atoms we can spend that negative charge over, the more stable it's going to be. So pulling out this proton is fairly easy. It's fairly acidic because the conjugate base is going to be fairly stabilized by multiple resonance structures. Okay? And so this is another one. So this one, we don't need a very strong base. You know what a good base to use this one? Again, remember we've talked about it, would be these. Even NaOH would work for this one, right? NaOH could be a good base to use for this type of one. Or sodium methoxides. Those are going to be strong enough bases to do this, to deprotonate this hydrogen to give us this enolate here. Okay, we can do that as well. So that's another way we can make our type of enolates. Another way we can do an enolate between these two, and we'll draw it up here. One more type of enolate is, what about taking how about an ester? We can take an ester. Again, use a base. Oops, do that completely wrong. Right? Even with our ester, we can take our ester, deprotonate that, to give us this enolate here, where it's a little bit, slightly very similar to our carbonyls, but we have an ester group there as well, right? This can work as an enolate, and we can do some chemistry on that as well. And we can talk about that. So these are typically the type of enolates that we'll see with either having aldehydes or ketones or esters, or having 2 carbonyls directly attached to the carbon, or even working with our nitrile group here. Those are different types of enolates that we can form, and then we can do some chemistry with them. In our future videos, we'll talk about ways we can then use these enolates to then attack different types of electrophiles, right? Here we can start thinking about, well, what type of electrophiles do we want to attack, right? Which things can we do? We have this great carbon source now that's going to work as a nucleophile, and now we can attack other things, right? Hopefully maybe attack other carbons, right? Make more carbon-carbon bonds. That's what we're interested in, making those carbon-carbon bonds. All right.